Alright, so if you'll notice from the example that we just finished up on the previous video, this example 5 here, that when you're doing your derivatives, not only do you have to know your derivatives of your trig functions, but you have to recognize that you have a chain rule. So kind of this is our general idea that we do with our trig functions. Here's the original rules as we learn them. And for some reason this book has its doesn't seem to like cosecant. For some reason it wants to do cosec, but it really should just be to the regular cosecant, CSC. So I'm just going to fix that so that the rule looks correct. So it would be negative cosecant squared, and the derivative of cosecant of x is negative cosecant x, cotangent x. I don't know how I missed, yeah. Alright, so over here are our general rules, the ones that we started with, the original, and then the only thing that changes over here is that we're applying the chain rule. That when you have sine of a function, which we're doing u equals f of x, and so what we're basically doing is doing a u substitution, finding du dx, and we know that with chain rule we take the derivative of the outside, cosine, times the derivative of the inside. So cosine u du dx. So that's our generalized chain rule for the trig function. So you do want to make sure you make your flashcards and not only have the original rule, but have it in the version of using the chain rule as well. All right, let's come down. We're going to finish up this packet through the last few examples. So example 6, and again, you'll start to see patterns and the types of things that we'll ask. We want to find the equation of the tangent line. Here's our graph, and we're at x equal to pi. So to find the equation of the tangent line, I need a point, and I'm going to need the slope. Okay, so to find the point, I basically need to calculate f of pi. So we're going to plug that in. So 2 sine of pi plus cosine of 2 pi, which simplifies sine of pi, the y-coordinate would be 0. So this will be 2 times 0 plus the cosine of 2 pi, which is 1. So we end up with 1. So the point that we're going to use is pi 1. And then our slope, of course, comes from finding the derivative, f prime of x, derivative of 2 sine of x, derivative of sine is cosine, so 2 cosine of x plus, now I'm going to apply my chain rule here, and these are simple enough. You don't really need to come up here and be like u equals 2x du dx equals 2. You can pretty much do that in your head. You basically are going, hey, cosine of u. Derivative of cosine is sine of the u times derivative of that. So we pretty much get our derivative, and then we want to find the slope at pi. So we plug in pi, 2 cosine of pi plus sine of 2 pi, and let's bring this 2 in front so it doesn't confuse us. Simplify, cosine of pi is negative 1, and sine of 2 pi is again 0, so we end up with negative 2. So the equation of our tangent line labeling it is going to be y equals negative 2 as slope, x minus pi plus 1. And then we're done with that equation. So a fairly straightforward example. The only difference is paying attention to the fact that you had chain rule with a trig function. All right, coming back to example 7 now, we're looking at using the table, and you're given certain values in the table, f of x, g of x, f prime of x, g prime of x. Now we saw a little bit about this earlier, but basically it's just practicing using all the rules. So if I want to find the derivative of 2f of x with respect to x, and I want to evaluate that at x equal to 2, the first thing I want to do is find the derivative of 2f of x. The derivative of a constant times a function is going to be 2 times the derivative of the function, and we're going to evaluate that at x equal to 2, which basically means we're going to go to f prime of 2, and that's where we start looking at the table. We find f prime of 2, which is 1/3, 2 times 1/3, or my final answer, 2/3. Okay, so just applying the rule. The derivative of a sum, so the derivative of f of x plus g of x, Derivative of a sum is the sum of the derivative, so that would be f prime of x plus g prime of x. And I like to use this little evaluate bar because then I don't have to rewrite stuff. I can just come in and go, hey, I'm going to evaluate that at 3, and I can put equals in between these and realize that I'm doing f prime of 3 plus g prime of 3, which is going to give me f prime of 3 is 2 pi, and my g prime of 3 is going to be 5. So there we go for that one. Now I'm going to leave product and quotient rule for you to practice and check your answers in class next time. Let's come to the more interesting one, which is f of g of x. So we want to find the derivative of f of g of x with respect to x. So we know that the derivative of f of g of x is going to be f prime of g of x times g prime of x. And so since we want to evaluate this, draw your evaluate line at x equal to 2, then basically all I need to do is calculate f prime of g of 2 times g prime of 2. So I'm pretty much going to go to the table. First I need g of 2. G of 2 is 2. So that would give me f prime of 2 times, now I need g prime of 2, and g prime of 2. G prime of 2 is negative 3 from the table, times negative 3. And now I need f prime of 2, so I go get that from the table. So I wish I had split screen. F prime of 2 is 1/3. So we end up with 1/3 times negative 3, which is negative 1. And again here, when I want to find the derivative of the square root of f of x with respect to x, it's going to be a chain rule. So this is f of x to the 1/2. So the derivative would be 1/2 f of x to the negative 1/2 times f prime of x. Okay, so that's just applying your chain rule. Notice that I'm not, you could go u equals f of x, du dx equals f prime of x, but you're basically going 1/2 u to the negative 1/2, take the derivative of the outside times the derivative of the inside. And I'm going to evaluate that at x equal to 2. So I would get 1/2 f of 2 to the negative 1/2 times f prime of 2. So I basically need to get f of 2 and f prime of 2. F prime of 2 was 1/3, so let's fill that in. F of 2, let's see what that was. F of 2 is 8, so we're going to put that in. So we have 8 to the negative 1/2, and then another half there. So now I just need to do the arithmetic. Square root of 8 is 2 square roots of 2. Let's just leave it square root of 8, but it's 1 over square root of 8. 1/2, 1 over square root of 8, 1 over 2 square roots of 2, times 1/3. So we end up with 1 over 4 times 3, 12 square roots of 2. All right, coming over to the next example. Now we have a quotient rule with a chain rule in here. So be very careful about this. We're going to do the derivative of 1 over, this is g of x squared. So I would probably, again with respect to x, instead of doing quotient rule, because that's kind of difficult, I don't really want to, so I'm going to do g of x and instead raise it to the negative 2. So I can do the derivative with just power rule and not have to worry about my quotient rule. So I'm going to do the derivative. It would be negative 2 g of x. Now we would have a power of negative 3 times the derivative of the inside, g prime of x. So we would have negative 2, and then my g of, and we're evaluating this. Let's add our evaluate bar at x equal to 3. Evaluate x equal to 3. Evaluate at x equal to 3. So we're going to do g of 3 to the negative 3 times g prime of 3. So we go get the values that we want to get for this one. And so g of 3 is -4, so -2, -4 to the -3, times g prime of 3, which was 5. Okay. And then if we need to, we can simplify. This ends up being -10 over 4 times 4 is 16. 16 times 4 is 64, and it's negative. So we get -64, which simplifies down to 5 over 32. Our example here, again, another derivative with a composition, actually composition within a composition. I'm going to do this as the derivative of f of x squared plus g of x squared, and that's all raised to the 1/2, and we're doing that with respect to x, and we're going to evaluate it at x equal to 2. So now just run through. I'm going to ignore this for the moment. I'm going to go, this is u to the 1/2. So the derivative would be 1/2 u to the -1/2 times, now I need the derivative of the inside, so I need the derivative of both of these. Again, remember you're thinking of this as f of x squared, so that would be 2 f of x times derivative of the inside plus 2g of x times derivative of the inside, and I'll put my parentheses. So this was 1/2 u to the -1/2, and this was the derivative of u. If you need to write it out and do u equals and do it in those stages, please do so. But the more you practice these, the easier it's going to be to make sure that we don't have any problems as we kind of do our chain rule problems. Let me just shrink this down just a little bit. It's called the cheat because I didn't leave myself enough room. Let's see if I can select that, move it over a little bit, and then go back to my fit to width because I need to evaluate this. Don't forget to write this at x equal to 2. And so basically what we're going to do is we're going to do 1/2 of my f of 2 squared plus my g of 2 squared to the -1/2 times 2 f of 2 f prime of 2 plus 2 g of 2 g prime of 2. And then we're basically just going to go get the information we need from our table. F of 2 is 8. 8 squared is 64. G of 2 is 2. 2 squared is 4 to the -1/2. Then we have 2 f of 2, 2 times 8, times f prime of 2. F prime of 2 is 1/3, plus 2 g of 2, 2 g prime of 2, which is -3. And then simply do our arithmetic to simplify this down. And so we should end up with, if this is a free response, you're actually done at this point, but just to practice, go ahead and I'll let you simplify this and just tell you that at the end of this, your final answer should be -10 over 3 square root of 68. Okay, and then our last example in this packet is, now that we have chain rule and we also know the fact that the absolute value of x is square root of x squared, I want to find the derivative with respect to x of absolute value of x. But instead of doing this as pieces and piecewise and dealing with it that way, what we're going to do is we're basically going to find the derivative with respect to x of the square root of x squared, which is what absolute value is equivalent to. So what that's going to allow us to do is use chain rule to find this derivative. So I'm going to rewrite this as the derivative with respect to x of x squared to the 1/2. Now I don't want to simplify this because that would have obviously absolute value of x and we go back. What I want to do is take the derivative using the chain rule. So this is u to the 1/2 So the derivative would be 1/2 u to the negative 1/2. And then you have times your derivative of your u, which is x squared, so 2x. And then if I do a little bit of simplifying here, this ends up being 2x over 2 square root of x squared, which would end up being x over absolute value of x. Now what that does for me now is it basically gives me a way to, instead of doing this in pieces, that I now have a formula for the derivative of the absolute value of x. Now we could have done this as a piecewise function. Since we know absolute value of x equals x if x is greater than or equal to 0, and the opposite of x if x is less than 0, then if I wanted to do the derivative of the absolute value of x with respect to x using the piecewise definition, basically think about what we'd have. We know that there's a cusp at x equal to 0. So it's not differentiable at 0. So we would only have x greater than 0 and x less than 0. And then if we look at the derivative of the left piece, the derivative of x is 1. And the derivative of the right piece, negative x, is negative 1. And if you think about what this does, this is exactly the same thing. That this would give me x over x if x is greater than 0. And notice that the 0 got dropped out because it's going to cause a division by 0 problem. And then you would get your x over negative x if x is less than 0. And if you simplify these, you'll get the same rule you got down there. So a different way of looking at it. But the idea here is to also illustrate that the absolute value function was not differentiable at x equal to 0. It was defined at x equal to 0. It was continuous at x equal to 0, but it's not differentiable at x equal to 0 because of the cusp. And notice that when I take the derivative, when I get to the derivative rule, f prime of x for this example is discontinuous at x equal to 0. It is undefined or does not exist. And that's this idea of differentiability. If the derivative is not defined somewhere, then f of x is not differentiable at that point. All right, so that wraps up our chain rule examples, and so we'll be working on this more in class.